Yeah, hi. I just decided I wanted to talk to myself, apparently, a little bit about what I'm doing. It was actually my brother that suggested that I just sort of try this because it might be fun. So, I'm well, I just finished my first year as an engineering physics student, and it was about 2 weeks ago, and now I've been doing some work. I'm working on a research project within nuclear physics, but mainly these last few weeks I've just I've worked a little bit on that, but also I've been taking it quite easy. I'm now sort of in the countryside with my brother and my parents, and my brother's very cute dog. So it's quite relaxed right now, and everyone's gone to bed, so it's very dark out. But I just thought, I'm spending all my time thinking about mathematics problems, and I'm learning a lot, both in my courses and now during these research projects. So I thought I'd just talk a little bit about that, just to sort of refresh my memory, see what my sort of lapses of understanding are. Um, and yeah, just sort of play around with it. And today I just thought I would talk about what I've been doing for the last, well, 1.5, 2 weeks probably. So I'm working on some nuclear physics project currently, which involves sort of selecting different nuclear mass models, and it's been done in a few papers recently. I think I'm going to link one of them below, which I've been reading quite closely. But obviously this is not specific to nuclear mass models, and it's more of a just... I had an introductory statistics course just before my course is finished, so I had my exam about 3 weeks ago, and it's been a really nice way to sort of keep reading these studies and papers and just keeping those abilities up from the statistics course by doing some fun side projects. So I just thought I'd talk for a few minutes about what I've been doing and what my very big problems are right now. So if you've taken some entry-level statistics at university, you've probably seen something like Bayes' theorem, right? So this is essentially the thing that I'm using right now, the basic approach of these methods that I'm applying, which is that the probability of an event A conditioned on B, so given that B is true, is the probability of B, given that A is true, times the probability of A divided by the total probability of B being true. And this is, I guess, pretty standard, maybe quite counterintuitive at first, but I think it's a nice theorem that we used a little bit in our statistics course, at least. And what I've been reading a few books and papers about is this parameter inference, which is essentially if we have some, in my case, maybe nuclear mass model, I've been able to do some fit using this method essentially. So we can say that if theta is some parameter in our mass model, for example, or some parameter in a linear regression model, or essentially whatever, and d is some data set or data, we can say that the sort of posterior probability of these parameters, given the data that we've observed, is equal to the probability of observing this data for a given, or for the given parameter values, times the prior probability of those parameter values. So we have some belief to start with, what we think the parameter values should look like. Maybe it's a normal distribution around a certain value or something like that, if we have some prior expectation of what we think it'll look like. And then we divide this by sort of the integral over the whole space of possible values of the parameter. So we essentially just normalize it with the probability of observing the data with any parameter value. And I think usually it's just as good to write this expression as a proportionality, there we go. So just say that the probability of a certain parameter value or set of parameter values given the data is just the product of the probability of the data for those parameter values times the prior probability of the values. So this is essentially quite simple, very easy to code. I think I'm using some Python package called PyMC. It worked great, as long as your model is not too slow. I used an external function at first. It was horrible because it was super slow and it took like 24 hours to run, and then I found I could speed that up by quite a lot. So I guess that's something to keep in mind. And that's, I'm having a similar problem right now, but I'll come to that later. So what I've been focusing mainly on this time is these mixture models, which is essentially that in this case, the above case, we probably have some model that we think describes the data very well, or we have one model that we're interested in at a time. But if we have, say, two models in this case, with a vector of parameter values, so perhaps we have the same model but with two different parameter values. I think that's pretty much what I've assumed here. Then we have that the probability of maybe one value of a binding energy or neutron separation energy, if you're into the nuclear physics part. So the probability of observing that value given your parameter values and some weight, W. I think it's also called like the mixture probability or mixture likelihood. Well, that's essentially your weight times your probability of observing this data y with the first parameter value plus the remaining weight times the probability of observing y with your second parameter value. And I guess that makes sense. It's like a linear combination pretty much, or a convex combination, I seem to recall it being called. So we have these weights summing to 1. And the nice thing here is that now we have two models and we're not quite sure which one describes the data best. That's essentially the point, which I probably should have led with. But then we can, similarly to before, just infer the weight as well as the parameter values given the data as, excuse the very bad writing here, but the probability of observing the data for a certain weight and parameter values times their joint prior probability. And I think usually we can assume these to be independent, so we just write P of W times P of theta, but yeah. And I'd also say that the probability of sort of observing the data is just a product of the probabilities of observing each separate data point here. And this works well, I think. But the thing that bothered me here, or the thing that sort of separates this from a recent paper, the one I've linked below, is that this sort of, if we're looking at some nuclear physics perspective where we have some mass models, this is a local mixture, no, sorry, a global mixture. So it's the same weight for all of these, which is like, it's good. It sort of points to which model is the most important, most interesting, but I'm more interested in sort of local features, as in the paper below, or I at least thought it was very interesting. So I think we'll turn the page here. We can use what I think is called hierarchical models for this. So we say that we have some sort of location parameter, essentially, which is just our number of neutrons and protons. If we're doing the nuclear physics case, I think it can be, anything else for any other scenario. And we have, in this case, I just use two models. So we have a weight vector and a vector of alpha values, which are like hyperparameters, because then I define, this is getting sort of messy, I'm very sorry, but we define these hyperparameters alpha because we have that the location dependent weight W is like conditioned on the location dependent hyperparameter alpha, and essentially given the alpha or a certain value of the vector alpha, this W follows a Dirichlet distribution, which is not something that we covered in our statistics course, at least, but from what I can tell, it's a very nice distribution for these sort of things. Very nice in Bayesian inference problems in general, but also very nice for this sort of weighing of different models, because we have these nice properties that both weights are within or like in the interval 0 to 1, and they sum to, that's not supposed to be a 0, that's supposed to be a 1, so they sum to 1. And we can also have like more, like a longer vector. We can have maybe 3 or 4 or any number of components here that we'd like. And I also wanted to sort of point out that the alpha is best expressed as some sort of function depending on our location parameter, which in our case is this neutron-proton vector, and some other random variable beta. And this is sort of where it gets fuzzy for me, and I haven't really, I thought I understood it until I wrote this up, and I realized maybe I'm not 100% sure. So I'll have to go through that maybe tomorrow if I have some time, hopefully. But it's sort of hard to balance doing this with relaxing with family, so we'll see when I actually do it. But yeah, so yeah, forgive the scratching out. I'm tired. It's very late actually. It's 1:30. But for this sort of hierarchical mixture model, we essentially have the exact same thing. So the probability of a certain data point y, given these weights, betas and thetas, are just the exact same thing as before, because the betas don't affect it once we have a certain location. So really, the W's here should have we can remember that they have like an implicit dependence on the location. And this is the thing I sort of just realized when I wrote this up, so I'll have to go back and think through this tomorrow, which is essentially that we can very easily sort of infer the parameters from one data point, because if we have a data point yi, the probability of, or the posterior probability of these parameters given this data point is just the probability of observing this data point given the parameter values w and theta times, and this is where the sort of hierarchical model comes in, that we have this w condition on alpha distribution, which we can use, times the joint prior probability of the betas and the thetas. And this is very nice, because then we can sort of find these values of betas to understand the location dependence, while still also getting these weights and the model parameters if we want them as well. And this is sort of my understanding of the paper, but I'm not entirely sure, because they don't really write this specific part out. And when you have multiple data points, like before, we just replaced this with a D, but the problem is that, well, the W's and the alphas are location dependent, right? So these might very well change. This is very easy to change. I'm not sure about this. I might just be tired to the point that I'm confusing myself. I'll have a look tomorrow, but yeah, I guess I'll get back to you later if I come up with anything, because the problem is, like, I have a code and it seems to work. It's just extremely slow and it's not working great. the results are like okay. Actually, they're kind of bad. Like the performance of the models are currently decreasing when I sort of mix them in this way. And that's not what should be happening, because, you know, when you have multiple models, you can mix them in a way that you improve the accuracy. So I think there's something wrong. And while I know this PyMC code to be kind of quick, but slow in the case of using these hierarchical models, for me, like, this is taking way too long. I don't have that many data points, and it's still taking like 24 hours to get an okay posterior distribution. And it's very hard to get anywhere when it takes 24 hours to run a test on like any change I do. So I want to figure out if there's something wrong, and I think maybe I'll just have to look into this tomorrow, because I don't know, could be something here, or I'm just way too tired. I'll have to find out when I wake up tomorrow. But yeah, in any case, this was, yeah. This is now a way longer recording than I thought it would be, but you know, I just wanted to talk about what I'm doing, and I at least had the hope of coming to some sort of habit of maybe spending half an hour each week just talking about what I've learned. And then when the courses begin during the fall, it'll be maybe a bit easier to come up with things to talk about. But, you know, right now I'm working on this, so I'll keep complaining that I don't quite understand it. But I guess that's also a very good way to point out that I probably have some things that I don't understand, which I now found because I had to explain this. So I guess the classical trick of you don't know something until you can explain it to someone else is very, very true in this case. But yeah. Anyway, good night. I'll see if I can come up with a good solution. I'd be very happy.